Okay. So for okay, I have a student asking if I can go over an email question that they asked me. So let me find that. Their question was about how buckets and B plus trees are stored on disk, and does it take up a block or what? So the answer is a little nuanced, but as just some vocabulary again first, a block is the smallest unit that a hard drive can work with. Typically, that ranges between 512 bytes and 4 kilobytes. Not variable on the same hard drive, but one hard drive might have a byte or block size of 512 bits, and another hard drive might have one of 4 kilobytes. So that's a block. A block is also the intersection between a track and a sector on the hard drive disk. A page, this, is the smallest unit of data that a database can deal with. In SQL, I think the default is 4 kilobytes. So it could be that one page could take up multiple blocks. So here, this page that I've highlighted in green is taking up 1, 2, 3, 4 blocks. Should be 8 blocks. Easy enough fix. Okay. Let's add more sectors. So this one block, or this one page, rather, is taking up 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. In this example, where the drive only has block sizes of 512 bytes, but a page is 4 kilobytes. Now, that means that, for example, if you have a table, I don't know, students, and one row of this table is, let's say, 256 bytes, then in one block, you could store 2 entries, and in one page, you would store 16 entries. So if this is the 0th and whatever, the first entry, first record or row, record, row. This is the second record, and all the way up to the 16th record. All of this could be stored in one page, and that would be the smallest unit that the database would get back. So if it only needs the 4th record, it will get 16 records, just because it returns the entire page. So this page is made up of 8 blocks in this example, and in this example, a table could take up one page with 16 records if the records are 256 bytes, and the page size is 4 kilobytes. Okay, so that's a block and a page. Now, for hash-based indexes, they deal with buckets. And a bucket is a page where you fit in as much as you can. So, and once it's full, then you need to create another point to secondary storage, which just means somewhere else on the hard drive. So in this example, let's say that John and Kara both get assigned the same bucket number, X. X is just a virtual number, okay? So in a file, there will be a position X, and you can fit in as many as you can into this bucket, but this is only 4 kilobytes. So, for example, I could have the pointer to John, and now he has a pointer to where his record is in the table. Kara also has a pointer to her record. And in this case, searching for either John or Kara is order 1, because you go to X and both of these are in the first bucket. But if you have many, many collisions, and f of, I don't know, zeta is also X, and zeta isn't in the first block, isn't in the first bucket, then first you will go to this entry X, you will look in this bucket for zeta, you'll find that zeta is not there, so then there's a pointer to another bucket. And this other bucket is another file on disk. So by going to that other bucket, you would need to access the disk more than once. And that is no longer order 1, it's something different. Harder to quantify, but not order 1. Okay. So as far as a, let's see. So this is the hash function here. And so each of these buckets is like a page. In this case, 4 kilobytes. And that's 8 blocks. Excuse me, not 4. That's 8 blocks. And so all of these can be loaded into memory at once, but after that, other buckets are stored on secondary storage, which is to say the hard drive. So you need to go to the hard drive again to access them. A B+ tree is stored also with pages. And the idea is to have the B+ tree have enough, it's a trade-off between how many values you can store in a single node. You could have a depth 1 tree and just have a really, really, really long node. And you could do that. That would make searching fast. The problem is with it that maybe that whole thing can't be stored efficiently. So, but you also don't want to just have like 1 entry, because then the tree's depth is going to be very, very long. And so it's a trade-off and a balance, and you have to figure out how many keys or how many entries you're dealing with, and exactly how many entries you want in this B+ tree. That is, do you want it to be a 10 tree or a 20 tree or a 50 tree? These are more on the order of that than a 2 tree or a 3 tree. They're much higher degree trees than that to make the tree shallow. But one node here doesn't necessarily have a relationship exactly to a block. It depends on how you define your nodes. And so there's a little bit of engineering that could be required if you're working at this low of a level for this stuff. Okay, so I hope that is clear. Okay, so that was a question that a student asked me earlier and then asked if I could share it with the class. So, any questions about that? So each block can hold X amount of records. Could be. It depends on the length of the record. If the record is smaller than the block size, then yes. In this case, one block could hold 2 records because one block is 512 bytes. In this example. But if the entries could be longer, the entries could be, or the records could be 1 kilobyte, in which case you'd need 2 blocks to store 1 record. So those aren't blocks, those are buckets. Okay, a bucket, these here are buckets, which is just the word that's used for hash functions. A bucket isn't necessarily a block. In fact, it's probably multiple blocks. But yeah, I mean, you make it, again, a sort of well, you could make each bucket 1 page, which would take up some number of blocks, depending on the hard drive and the block size. So here, this, 1 bucket could equal 1 page, which would equal 16 blocks on disk. Yeah, okay. So, yeah, part of it's just having the vocabulary, understanding like a block, a page, a bucket. I mean, they're all different words that sometimes can have some overlap, but yeah, okay. Fine. So let's go back to entity relationship diagrams. So we have entities that are rectangles. Entities are connected via a relationship. That is a triangle. Relationships can also have attributes. But the entities must have at least one keyed attribute. That is to say that any entries for that column have to be unique. The way that entities are connected with the relationship, they're connected with what are called participation constraints. That's a thin line, a thick line, a thin arrow, and a thick arrow. Unconstrained, meaning you could have total participation, no participation, partial participation with members of that entity and the relationship. Or otherwise, you can say that everything has to participate at least once, or at most once, or exactly once. So today we're going to give a little bit, a few more examples of entity relationship diagrams, and I want you to try to come up with the tables that would correspond to them. Generally, it's very straightforward with the entity. because for the entity, you can have the name of the table. That's the name of the entity. The number of attributes are the number of columns, as well as, and the names of the attributes are the names of the columns. And the key for the table is whatever the key is for the, whatever the keyed attribute is for the entity. The part that's a little bit trickier is the relationship, and capturing the participation constraints with tables and keyed values. There are too many combinations of participation constraints, and so I won't go through every one of them. There's 16 if you wanted to count them all, or maybe 8, and then say that the other ones are just symmetrical. But I'm not going to go through 8 of these. Okay, so we talked before about how you should always consider the relationship that's connecting these two entities as being like a two-way street. If A has a relationship with B, then you can think about that relationship in terms of how does A relate to B, but also how does B relate to A. So here, the yellow one is talking about the books that people like to read. So, is every book here a book that somebody likes to read? Could be. Here, this relationship is about how people relate to books. So entries in here that I'll just put a dot for, that would be a person. That this is a person. Does this person, must all people like to read a book? It could be. It depends on how you want to define it. And however you want to define it, you can capture that with the type of participation constraint. Okay, so ER diagrams have participation constraints. Tables or relations have key constraints. The goal of ER diagrams is a way to help figure out which keyed constraints are going to be useful for whatever. So this is the simplest example, I think, when you have two unconstrained relationships. What that means is that there could be no participation, partial participation, or total participation. Anything's okay. And by participation, I mean entries here, records. Do these records have to appear in here or not? That's what I mean by participating. So here, I'll say title A, B, and C. And here's people, A, B, C, D, E. Okay, now, because it's unconstrained, that means that, for example, this book C, nobody likes to read it. That's okay. It doesn't have to be there because this is unconstrained. So you can have partial participation. This is what's called partial participation. A is participating 2 times, B is participating 1 time, and whatever. Okay. And likewise, for people, that's unconstrained. So you could have an entity appear no times, like C, D, and E. These are people that apparently just don't like to read books. That's okay, according to this diagram, because it's an unconstrained participation. You can also have one record, I'll do this one record participate more than one time. So this person, B, appears 2 times. They have 2 different books that they like to read from this list of books. Similarly, here you can have multiple participation for book A. Book A is liked by more than one person. And okay. Now, here, this relationship here and the constraints are both being captured in this table. And that's not actually quite right. Here, this should be a compound key. So you can have a composite key or a compound key. I might be mixing these 2 words up, actually. If somebody knows for sure and I'm using it wrong, let me know. But, okay, so there is a difference. Okay, if this is my table, and I haven't yet chosen the keyed attribute. This is example data. And here, if I make just the title the key, then this entry is problematic because now A appears twice, and that shouldn't be allowed with, I'm sorry. So A appearing twice would not be allowed if the title were the only key. So that can't be the only key. Similarly, name can't be the only key because we want one person to like to read many books. So this is going to be, you combine these together to be one key. It's the pair now. So this entry is okay because although they agree on the title of the book, they disagree on the name. So as a pair, these are different things. Similarly, this entry is no problem. It's okay to be there because although these conflict in this column, this person likes to read more than one book, the books are different. Okay, so that's this sort of compound or composite key. I have to look up. One of them is if you have a key like this, like I just described. Another is if you have keys like this, where you can have more than one key. In this case, it would have to be a book can only appear at most once, and names can only appear at most once. So if these were the keys, then this entry would be bad because of the title, and this entry would be bad because of the name. So if you key things like this, then you're making sure that people can only appear exactly or at most one time, and books can also only appear at most one time. But we don't want that. We want it unconstrained. A book can participate many times. A person can participate many times. So we have both of the, we combine these keys to be one key. Okay, questions about that? No? Okay. Then I will give you a ER diagram, and I would like you to come up with the tables for it. Okay. Let me come up with something. Okay. I'll keep it with books and people, I guess. Okay, so this is going to be about books that have been read by people and people who have read certain books. So books, this is going to have a title, it's not a social security number. What's it called for books? The unique identifying, ISBN, that's it. ISBN, because you could have a book with the same title, but not with the same ISBN. Title and author, who cares? Okay, people, they have name, social security number, and I don't know, income. Okay, now here I'm going to say that we only, like, okay, maybe this is like a library that we're making for these people. So, no, that's not quite right. Okay, whatever, it doesn't matter. I'll just make it up. So, here, this is saying that books, each book has to be liked or have been read by exactly one person. Okay, if two people read this book, it's not in this book or in this pile of books. These books are ones that have been read by exactly one person. And for people, they have to have read at least one book. Okay? And just because, I'll put date here. That's the date that the person read the book, that they finished the book, whatever. Okay, so that is the ER diagram, and I would like to give you a couple of minutes to figure out how to capture this in using relations or using tables. So I'll give you until, I don't know, I'll give you 5 minutes, so 2:17. And please do actually try this, get out a sheet of paper and, do it. Even if you get stuck, it's good for you. Okay, so I'll check in with you guys in 5 minutes. So I'll repeat that then for the recording, sorry. Okay, so right now we're just capturing this constraint here that says that books must be read exactly one time. The way that we're doing that is we're actually combining the has read and books into one table. So the book being read, let's see, because the ISBN, where did it go? What just happened? Okay, because the ISBN is a keyed attribute, any book is going to appear at most one time. Therefore, it can never be read by more than one person. That's what this is doing, okay? So a book can never be read by more than one person, but it has to be read by at least one person. So we have a social security number, and we don't key this. If you did key it, then that would, for example, make these rows conflict. But there's nothing in the ER diagram that says that a person can only read one book, just that they have to have read at least one. So this is not keyed. And by adding this column to this table and saying that it can't be null, then that means that every book, which only appears exactly one time, will also have some person who has read it. Okay, and yeah, okay. Now for the people table.
Quick question.
Yes.
If it was a compound key between ISBN and SSN, wouldn't those rows not conflict?
If it was a compound key, you mean like this?
Yeah. So like it'd be the 1 and then the 1 1 whatever, and then the 2 and the 1 1 1. Since they're two unique combinations, wouldn't that not conflict?
Yeah, sure. I mean, this would, hold on. No, this would be a problem. Because then I could do this. Let's see. Hold on, let's see. I could do that too. And now this is okay because it's a compound key. And so it's okay for this 3 to appear twice because here these disagree. But now there's a book that has been read more than one time. But we don't want books that are read more, that can be read more than one time. We want books that have been read exactly one time. So if you make it a composite key, then that would allow for these two entries, but that should not be allowed. Make sense? Each book is read by exactly one person. Yes. Oh, a foreign versus composite key. So this, right now, is an example of a composite key. Okay? So it's when you're keying on more than one attribute. So now the key is not just ISBN, and it's not just SSN, it's the combination of the two. So long one of them differs, then it's okay. So for example here, that's the same entry, but it's okay because they have different ISBN numbers. Similarly, these are okay because they have different social security numbers. So it's for the pair or the pair or triplet or whatever it is, however many things you're making the composite have. The line from people to have reads means that each person has read a book. Yes, each person has read at least one book. Okay, but and I'll get to the foreign key in just a minute. But first, I want to make sure that it's clear why you do not want to have a composite key here. Again, it's because this says books are read exactly one time. And if you make that a composite key, that would allow for books to be read more than once, that we don't want. So instead, if we make ISBN the only key, then, if I wanted to add, this book here again, that would conflict and not be allowed, which is what we want in this case. Okay. Okay, so for a foreign key, before I finish the people table, this is also a foreign key. So SSN shouldn't be a composite key, but it is a foreign key. What a foreign key means is that it refers to some other column, in this case, this column. And what that means is that every entry here has to come from this pool. Okay, this pool of social security numbers. Let's say that these are my pool of social security numbers. Okay, I can write this number because it appears here. So that's okay. It's coming from that pool. This number is okay as well because that also exists in the pool. What would not be allowed is if I wanted to do 8888. This would not be allowed because there is no 8888 here. So that's what a foreign key does. Okay, I see a question about, for this table, what's the difference between the thick arrow and the thick line? The thick arrow, this means exactly 1. So every book is read by exactly 1 person. It's not allowed to have 2 people who have read the same book. Where the thick line is at least 1, which means that a person must have read at least 1 book, but they might have read more than 1. In this case, like here, each of our 3 books, books 1, 2, and 3, all of them have been read once. All of them have been read by 1 person. Books 1 and 2 happen to have been read by the same person, but that's okay. Well, actually, this isn't quite finished, but yeah, you could have 1 person have read more than 1 book, but a book can only have been read by exactly 1 person. Foreign key is on 1 attribute, correct. They tend to have the same name. They don't have to, though. I mean, I could call this, person SSN. I could call it something else, but when you, I don't know, whatever. It's a side note. Okay. So we're almost there. We've captured this, the exactly 1, but now we're missing this. The person reading at least 1 book. So if I just left it here, then this would be a problem because here's, 3 people who haven't read any book and hasn't broken any rules. So I'm going to add ISBN here. And I'm also going to say that this is not null. This is going to be a foreign key to that ISBN. And there is, let's see, should it be keyed? I believe so. Yeah. So this is keyed. Not a composite key, but these are like 2 independent keys, which means that here in this column, the social security column, a social security number can appear at most 1 time. Similarly, because I'm also keying on this, any book can appear at most 1 time. And here I want that to be keyed because books can only be read at most once. I'm sorry, by at most one person. So I do not want, let's see, so here, 1 has read book 1, 2 has read book 3. And now notice, there's a little bit of a difference between these. Here, 111, this person has actually read 2 books that we can see here. Okay, 1111 has read 2 books, but we're only recording one of them in the people table, because we only need 1 to ensure that this person has read at least 1. If you want to know all of the books that they read, then you can visit the books have read table. But here we can put at least, like whatever the first book is, or one of the books that they've read. And because that cannot be null, then everybody will have to have read some book. I can't do this and say that only 2 people have read books. That's not allowed because I specified that it's not null. So let me do this. 4, 8, 7. And here, we have here. Okay, and now that's it. So, I'll go through it again. And like I said, this is a harder example than I thought. But you'll have to, if anybody got this, let me know, because that would be great. Okay, so for this relationship, where we can enforce, and in general, this is what you do with an exactly 1 kind of requirement, is that you take whatever that is and put it in the table that it corresponds to. So in this case, books has to have been read by exactly 1 person. Well, we know in the books table, each book is going to appear exactly 1 time because that's what it's been keyed on. Now, for each of these books that has been that appears exactly 1 time, we're saying that there has to be a social security number associated with that book, and that cannot be null. So that ensures that every book has been read. And every book appears exactly 1 time, therefore every book is read exactly once. We do not key on the social security number because there's no restrictions on 1 person reading many books, just that books must have been read 1 time. For the people, for this one, saying that people have read at least 1 book, you can add the ISBN column to it. It's okay that not every book that they read appears here. Like, for example, this person, this is only a record of 1 of the books that he's read. He's read more, but it just has to be at least 1 of the books that he read, because this also cannot be null. Let's see. And we make this one, we do make a key, not a composite key, mind you, okay? Because that would be any one of the 2 pairs that's different. This way, it means that any number can appear here exactly once in the social security number, and here, all of these numbers has to be unique. So it's just enforcing a uniqueness constraint on every entry of each of those columns. And we want that for the people table because books can only have been read exactly 1 time. So it would be a problem if a book were to appear here more than once, because, if we had this. then that's now violating this constraint that books have been read exactly one time.
How would you have two keys in one table isn't a composite key? Because in MIS, we for every single table we ever did was only one key or a composite key.
You can do this too. And here's an example of why you would want to. So the way that it would work is when you're creating a table, let's see if I can. Make that bigger. I know it's very small. Oh, it's still small. That's better-ish. So when you're specifying a key in a table, if this were a single key, it would just be like this. If it were a composite key, like if I did that this is a composite key, and this would be this type of key, where it's a composite of both of them. This is the pair. But sometimes we don't want that. Like in this case, we don't want a composite key because that would allow a social security number to appear more than one time, and we don't want that. Also, it would appear a book to appear more than one time, which we also don't want. We only want social security numbers appearing exactly once, and any book in this column we want to appear exactly once. So the way that you do that is with this key. Now, when you're defining this, you can only have one primary key, but you could have a unique one. So this is how it would work, unique ISBN. So unique is kind of like just declaring another primary key. So that's this unique word. If you look it up this exists in the SQL language, and here's why. Because like in this example, it would be required in order to have all these constraints. Yeah, you might not have seen it before, but yeah, it's there. And I mean, it's, I think it's common enough. Yeah, I don't know. I don't know how broad it was in MIS. Does the book have read feature every social security number?
Sorry, I think that was a bad way of like writing the question, but what I meant to ask was if you have a foreign key, is every single, like, will every single social security number that's featured in people be featured in books have read?
Not necessarily.
Okay.
Yeah. Let's see. This would be a bad example because of the constraints that I put here, but yeah, not necessarily. For example, up here. Sorry, I should have added this before. This is a foreign key. That's a foreign key. So here, there's names, C, D, and E that don't appear here, which is fine. They don't have to, because it's unconstrained, this relationship. And a foreign key doesn't require that everything is used, just that whatever is used is coming from this pool. You can't add an F or a G or different names. They have to come from here. That's all that a foreign key means.
So are we not using, like in MIS, we did like one to many and then many to many, and we looked at relationships like that. Are we not like directly using those types of symbols here?
Those types of symbols. You might have learned a different type of ER diagram. than the one, in particular, the way that the participation constraints are made. But that's implicitly here. This is a one-to-one. Right? If it's exactly one, then that means that every single one has to have a connection. So that's a one-to-one. This thick line would be a many to one. So that is to say, one to many, one to many.
Is there a name for like this type of notation that we're using versus what we used in MIS?
I don't know what you used in MIS. This is, I mean, it's the notation that's used in this book for ER diagrams. This is an older book, but I mean, it covers, I mean, nothing's changed. You might know a different ER, different, I don't know, way of writing an ER diagram, which is fine. I don't really care. I guess in this class, it would be helpful if you just adopted this just for consistency, for internally for this class. But in general, I mean, they're all the same thing. It's just that the notation's a little different. I'm just sticking with this notation because I'm loosely following this book, and I wanted people to have a reference. So, and I don't want to stray from the reference material. So yeah, guys, it's past the end of class. So you can go ahead and sign off if you like, and have a good week. I will see you on Monday.